All right. Hello, everyone. It's great to be here. Thanks, Paris, for the introduction. As Paris mentioned, today I'll be talking about my most recent project, which is called Pravega. Been working on it for the past year with my colleagues back at Dell EMC. So hopefully you find it exciting. You know, give me lots of feedback, and in the future, perhaps even running this in production. Who knows? Before I go into the specifics, let me give you just some context for Pravega, what I'm going to talk about, and so on. Pravega is a stream store that is core to a platform, a stream data analytics platform that we are building. So there is a broader effort that in the team, which is building this platform, and Pravega is one piece of it. It's a very important piece. I would say it's the core of the platform, and that's the main part that I'm working on. Now, about Pravega itself, there are a few things in this stream store that we wanted to achieve. First, to be a stream store, it needs to be a data store that can accumulate the stream data that is being continuously generated. And there are a few special things that we wanted to have. First, we wanted to be able to store data permanently. I mean, the state today is that you ingest data, perhaps say with Kafka, and then later you move to HDFS. Or you're just moving data around storage dependencies. And one of the things we'd like to achieve is to have one single store where you ingest the data and the data just lives there. If you want to delete, it's your choice, it's your application, but ultimately you can have it there. We want to be able to accommodate an unbounded amount of data on a per stream basis. So if you have a stream that has been running, I don't know, say for years, you want to be able to accommodate all that data if you choose to. We also care about order. So if your stream is based on events, I don't know, messages, records, or whatever abstraction your application cares about, we want to preserve that order because that might be important for your processing, for your application. And finally, in the world that we don't know when spikes are going to strike, or we have changes in the workload, we must be able to accommodate such changes. So we want our system also to be able to accommodate to that varying workloads that we often see in production systems. All right, so now let me step back and talk a bit about three important terms that I'll be using throughout the talk. Yeah, I just want to make sure we're on the same page about this. So when I refer to stream, I'm talking about data that is being continuously generated, events, messages, records, whatever your application cares about. When I talk about logs, I'm referring to the specific append-only data structure that we use often in systems to store such stream data. It's a natural data structure when you talk about streams, because as stream comes, you append it to this data structure. So it's a very natural way of, even implementation-wise, of representing such stream data. And finally, for storage purposes, it's often useful to think of chunks of these logs. So if I chunk a log up, then I'm able to store it more easily because I can move those chunks around. So I'm calling that a segment here. So three terms: stream, log, and segment. And I will start talking about logs. In fact, I apologize in advance because it's going to be a bit of a long introduction, but I think it makes sense to cover all the past work that I have done in logs to show you why we got into what Pravega is today. So logs in retrospect. It dates back to, I don't know, maybe 10 years ago when I was working on replicated state machines, fresh out of grad school, all happy about it. Just work on distributed computing concepts. Replicated state machines, you don't need to know specifics about it. But the core thing I want to show here is when you implement a replicated state machine, what you need to do is you have to define your state to start with. Your state is just a set of variables. And to make sure that that state is consistent across replicas, because that's what I'm trying to build, a replicated service, you run a protocol to keep a log consistent. So each one of those replicas is going to have a copy of this log, and we're going to run a protocol, typically an atomic broadcast protocol, that will keep that log consistent across replicas. And that's essentially what systems like Zookeeper do. So Zookeeper is a replicated state machine where the state is this hierarchy of Z nodes. In each one of the replicas, if you go to the code, you're going to see a transaction log there. And ultimately, that's what Zookeeper is doing. So it has this protocol to keep that run across servers, replicas of the service, to keep that state consistent. And the way it does it is agrees on the operations that need to be applied to the state, so that the service, all those replicas can have a consistent state. Now, back in the day, we were having conversations about what kind of use cases would make sense for Zookeeper, or even people were thinking about what use cases would make sense. We got into conversations like the following. Well, hey guys, on the phone, yeah? Hey guys, Zookeeper is bad. All right, that's very possible, but why is that bad? Well, it's bad because I have this use case where I'm trying to use Zookeeper as sort of a journal, right? Oh, that must be metadata, right? So if it's metadata, it's good for Zookeeper. And so I have this kind of journal, and it's really write intensive, and Zookeeper just doesn't give me like very good write throughput. So yeah, that makes sense. Zookeeper is not really designed for write intensive workloads, and in fact, we always tell applications to not have writes to Zookeeper in the critical path of their operations. So yeah, Zookeeper is bad because it doesn't satisfy my use case, which has metadata that I need to persist. And yeah, it's not doing what it tells me that it does. It's a valid use case, but if you think about it, or at least when we were thinking about it back in the day, there was no real good system to do it, to satisfy this kind of use case, to have write-intensive workloads in the critical path of your operations. And so we ended up doing a second system in the Keeper family, which was Apache Bookkeeper, where the idea was to move the agreements that you have upon every write to Zookeeper to the end. The way we did this was the following. We have the servers that we call bookies. You have a single writer. You create a log in Bookkeeper. A log is called a ledger, and you just keep appending to that log. There is no coordination across the bookies. That's actually closer to if you're in the distributed computing area, it's closer to register protocols rather than state machine consensus protocols, and it's more suitable for write-intensive workloads. Now, another interesting thing, which is related to what I mentioned, that we are moving Zookeeper operation out of the critical path, is that we do have a close operation because we need agreement on the content of such a log. If I have two readers that go read the content of one of these ledgers, we want to make sure that they read the same content. So we need agreement at least at the end on the end of that ledger. And for that, we have this close operation, which all it does is write to Zookeeper, right, the last entry that has been written to the ledger. And with that, we moved Zookeeper operations, write operations, out of the critical path. We still have agreement on the content of the ledger, and this is very good for write-intensive workloads because, again, I'm not coordinating across servers and such. So, very simple idea. But then one question to ask here is, well, if I do this, isn't it the case that I'm limiting the amount of data I can store per ledger to the capacity of one single bookie? So if I keep adding entries to those bookies, isn't it the case that eventually I'm going to hit the capacity of the bookie and I won't be able to write anymore? It is true, but one of the interesting things is that because I can close ledgers, I can do something like this. I can logically close a ledger, create a new one, close a ledger, create a new one, essentially rolling those ledgers and logically stitching them together, forming an unbounded log. Right? So having this ability of closing, having agreement at the end of each one of those logs enables me to have an unbounded amount of data for this logical log. Even though Bookkeeper itself doesn't expose it, it does give you that ability. And just mapping to the terms I mentioned in the beginning, you can think of each one of those ledgers as a segment. Now, to cover use cases a little bit for Bookkeeper, so what motivated us to do this? I mentioned abstractly the journal case in that dialogue, but there were real use cases that motivated us to work on this. One was HDFS. At that time, name node was a single point of failure. It was a big problem. You had like 2,000, 3,000 node clusters depending on this single name node, which would crash sometimes. It was not a lot, but it was enough to cause trouble. So the solution we proposed, which was actually partially adopted, was to use Bookkeeper for storing the edits log and using Zookeeper for failover, and that would give you automatic failover, which is nice. But with respect to logs, that's good. It's one log that I would use in this case, but is there any need for having multiple concurrent logs? Also early on, we came across this use case, which gets closer to the data domain, where we had topics. We wanted to do scalable pub/sub. So we had topics, and we wanted the messages published to those topics to be durable. Semantics was simple. There is no different options here. You publish messages durable, and you can consume it anytime you want. And each one of those topics would persist the messages in a Bookkeeper ledger. And so if you had many of these topics, then you would need many ledgers. And the use case for this, actually, I have to say that we implemented a prototype for this, which was called Hedwig. It was open source for some time as part of the Apache Bookkeeper project, but we removed it in the end because no one was using it, and so maintaining was a problem. But that prototype existed, and if you go to the logs in Apache, you see it. But the use case we had for Hedwig was a key value store that we had at Yahoo called Sherpa. That key value store was split into tables. So each one of those tables would use a topic, and each one of those topics would persist that to Bookkeeper. The reason for using a topic is that we wanted to propagate updates to the table across regions. So that was a geo-distributed key value store that we had. That forced us to think more carefully about the design of bookies, because we didn't want to have, so if I'm talking about hundreds of thousands of topics, I didn't want to have to use a different bookie ensemble for each one of those topics. That would be too much harder. So we needed to consolidate all those ledgers, all that writing into the smallest set of bookies possible. So we ended up with this design that we have two devices in each one of the servers, in each one of the bookies. One is the journal that we write synchronously to, and another is the entry logger, which you write asynchronously to. So the journal is used only for recovery, otherwise you'd never read from it. And the entry logger we use for serving reads to Bookkeeper ledgers. This graph here is to show how well that worked. If you see the black line at the top, it shows throughput as we increase the number of ledgers, and you can see that's pretty much flat. It doesn't matter the number of ledgers you're writing concurrently to. But the two other baselines show that if we use like a naive design where we have separate files per ledger, then we end up sacrificing performance as we increase the number of ledgers. All right, this is great for write-intensive workloads, but what about reads? This is not so great for reads. And that's one reason why Apache Kafka has chosen like a different path, because they wanted to be able to serve reads fast as well. And so they ended up with this design where they use independent files for each one of the partitions they have in a topic. So Kafka has this topic abstraction, partitions as part of a topic, and what is stored in each one of the brokers is a topic partition. But they had to sacrifice a few things. So first, there is no guarantee that a message is actually persisted when you get an ACK. Even the strongest option, there's no guarantee that is stored on disk. You can configure the server to do it, but the performance won't be great. So out of the box, you won't do that for you. There's no notion of closing a partition. So you cannot do the composition that I was mentioning before that we can do with Bookkeeper. Data in a partition is limited by the capacity of a server. That's part of the problem with not being able to close. I cannot close in one place and continue in another. It all has to fit in a single server, which is fine for the Kafka case because it was really designed to be storage for temporary data. Just store data temporarily as you ingest but later on you move that somewhere else. And finally, it has a rigid partition scheme. So you cannot really compose partitions in a way that I'll explain with Pravega in a moment. So topics have a set of partitions you can increase perhaps, but you can do much more than that. So far, what we have seen out of these three systems that I mentioned. Just to conclude this part, and then I'll move into the specifics of Pravega. Apache Zookeeper implements a log, but that's hidden behind the state of Zookeeper, which is this hierarchy of Z nodes. The replication is heavyweight, so it's not really ideal for the kind of logging that we wanted to do. So we moved into doing Apache Bookkeeper, which provides like a lot of these logs that we call ledgers, and enables us to logically concatenate them to form like an unbounded log or an unbounded stream. It misses a few things. It misses the manipulation of segments, right? So all that logical concatenation I was talking about, it doesn't do for you. You have to do that yourself. And it misses on the read throughput side. If you're trying to do catch up and you have to read a lot of data from Bookkeeper, that might not give you the best read performance ever. And the reason is simple. We have this entry logger where we're interleaving data, and if you read it, you read your data plus data from a lot of other ledgers. So the read throughput is not super efficient. For Kafka, the whole messaging story made sense. There are lots, it's very popular, lots of applications use it today and will continue to use it. But it has made some choices that are far from ideal, and we think we can do a lot better. One is sacrificing durability. Second is constraining the amount of data in a partition by the capacity of a server. And finally, having this rigid partition scheme that doesn't allow you to manipulate segments and compose them in different ways. All right, so Pravega. At a very high level, that's what you expect. Pravega provides you this abstraction of streams where you can ingest data to. So when you ingest data, you just append data to that stream, and you can consume stream data on the other end. Internally, a Pravega stream is composed of the segments. So the segment is the unit of a stream, which is the definition I have given in the beginning. It's an append-only sequence of bytes. What are the things that we can do with it? One of them is, an obvious one even, is the same thing that Kafka does with partitions. You can put them in parallel, you can put the segments in parallel, and whenever you append, you can route your append request according to a routing key. But segments, different from Kafka, different segments can be sealed, like we do in Bookkeeper. You know, as you can close a ledger, here you can seal a segment. And when you seal a segment, you cannot write to that segment any longer. But then you might be asking, well, okay, that's great, but how is that sealing useful? Well, it's useful because I can compose segments. One very basic way is I can get two sealed segments, concatenate them, concatenate an open one, and all of a sudden I have a longer stream than I used to have. And in fact, I can concatenate an arbitrary number of those sealed segments and have an unbounded amount of data for a single stream. And those segments can be spread across a cluster of servers. So there is no constraint with respect to the amount of data or even the capacity of serving in parallel the segments. But it's not only this linear composition that we can do. We can also do parallelism here. So if I have, I can take two of the sealed segments, put them together, in parallel, concatenate a new open one, and that would correspond to merging two segments. Right? So if a segment, for example, is cold, it's not getting enough data, I can merge it into one so that I can save resources in my system. And that's in fact some of the things we do. So here are a couple of things that we do in Pravega, features that we provide. We can scale a stream. So by scaling a stream, I mean, if I start, say, with a single segment, and that segment becomes hot, I can seal that segment and create two new ones. And now I have more parallelism in my stream. I can keep increasing this forever if I want to, right? And that would adapt to my ingestion workload. One nice way of observing this is look at this diagram where we have routing key space versus time. If I start with the same single segment, say segment 1, let's say that at time t0, I notice that it's hot. If it's hot, then I split it up into 2 segments, 2 and 3. 2 keeps going, 3 keeps going. At some point, I realize that 2 is hot again, so I split it up into 4 and 5. Eventually, 4 and 5 get cold, they're merged back into 6. So I can have this sort of dynamics in a stream, all according to the ingestion workload that I have. And Pravega will take care of changing the mapping of the routing key space into segments for you. So there is nothing that the application directly needs to do. And as you observe, this will change over time. There is no static mapping here. This is essentially the same graph as before, but from a real cluster. This is what we expect a stream to be in production with respect to scale up and scale down events. So the colors represent how cold or how hot the segment is. Bright red means hot, light blue means cold. And when they're cold, 2 neighbor segments are cold, we can merge them. If one single segment is hot, we can split it up. Here are 2 examples of a scale up and one scale up and one scale down event in the graph. So at the bottom, we see one that was hot and was split into 2. And at the top, we see 2 neighbors that were cold and were merged into 1. So that's scaling a stream. The next interesting feature we can do is transactions. So with transactions, what you want to do is make a bunch of appends, but you only want to expose that data once you commit it. So before, you don't want to expose that data. So what we can do with Pravega, with again this flexibility of manipulating segments, we can create temporary segments for the stream. For the transaction, each one corresponding to one of the parent segments. Whenever the writer appends to the stream through the transaction, it's going to write to those temporary segments. And when it's ready to commit, we just go, Pravega internally will go, seal the segments, and merge them back into the parent segments. Now, one advantage of doing this is, say, I abort the transaction instead of committing it. In that case, I'm not polluting the primary segments of the stream with unused data. In this case, I can just discard those temporary segments, and the data is gone. So it's as simple as that. As for the functionality itself, in Pravega, today the scope of a transaction is a single stream. You cannot do transactions across streams, but there is no limitation with respect to what you can do for a single stream. You can append to all segments. There is no limitation on the keys in the key range, and that can be interleaved with regular writes to the stream. For the reason I mentioned before, because again, the transaction writes all go into temporary segments. And this transactions is important in this space because we want to be able to avoid duplicates in partial state, for example, in the presence of writer crashes. So if your writer was supposed to write 10 messages, he wrote, I don't know, you're not sure if 5 or 6, then you might as well just abort and start from scratch. So that's one of avoiding partial writes or duplicates as part of the data that is going downstream. Now let's have a quick look at the architecture of Pravega, what's going on under the hood. So at a very high level, there are 2 key components that we implement. One that implements the control plane, which is called the controller, and the other that implements a data plane, which is segment store. The controller is responsible for doing the stream lifecycle management, creating, deleting, scaling, and also for transaction management. Now, the segment store knows nothing about streams. All it does is create segment, delete segment, append data to segment, which may not sound very much, but it's actually a lot. But the separation here is segment store is kind of the muscle of the system, right? It does the real hard work, while the controller is actually the brain who is just commanding the segment store. And that's essentially what it is. So the figure I showed before of Pravega being a segment store, where I have sealed and open segments, is implemented with these 2 main components, one being the controller, the other being the segment store. Now, since I mentioned I mentioned that the storage dependencies before. I should say a bit about it in how it works in Pravega. So in Pravega today, the segment store uses two storage dependencies. One is Bookkeeper, which it uses as a journal, and it writes synchronously to that journal. So every append to Pravega is made durable. Actually, you have no other choice. That's the only option we give. And asynchronously, we move data into this long-term storage, which we call tier 2. So the difference between the two with respect to the properties they provide is that the first one gives us low latency durable writes through Bookkeeper, while the second one gives us just plain high read and write throughput. And the reason why we care about especially high read throughput is that we want to be able to do historical and catch-up reads fast enough. So if you have a reader or a consumer in your application and it's lagging behind, but all of a sudden needs to catch up, then you must be able to pull data fast enough out of Pravega. The last piece of Pravega I want to touch upon, which is interesting, is the state synchronizer. So the state synchronizer allows us to do the replicated state machines I was talking about in the beginning, but in a much more fine-grained manner. So what we do is we provide in Pravega the ability of conditionally appending to a segment. And that gives you the ability of implementing a replica set in your application. If we look at the figure, the replicated state machines figure I had in the beginning, what we are really doing here is separating state replication from log replication. So now with the state synchronizer, the state replication is done by your application, while the log replication is done by Pravega. So if you remember the Zookeeper figure, that was all done in one system. And now doing things this way has the benefit, again, of being able to implement coordination-like tasks in a much more fine-grained manner. So in the old Zookeeper world, if you're doing like leader election, group membership, metadata management, you would do all that in one single ensemble. And here you can split them up into different tasks. Each one would be using like a different segment. And this is very nice if you are in an environment where you have lots of applications or lots of these tasks, and you can separate them out like this. All right, so I'm ready to wrap up. I talked about a lot about systems that were not actually Pravega itself. Talked about Zookeeper, Bookkeeper, and Kafka, but I wanna leave the message about Pravega because that's again the main thing, the main goal of this presentation. So Pravega is a stream store. Stream store in the sense that we want to give applications the ability of ingesting continuously generated data efficiently. There are a few specific things that we have in Pravega and we are working on, which is not to limit the amount of data in a stream to the capacity of a single server. It's also designed so that your retention doesn't have to be 7 days or a month or some limited period of time. So architecturally, we would like to give you the ability of storing data for as much time as you like. Obviously, there are practical limitations like the amount of disk space you have, but in terms of architecture, there is nothing that prevents you from storing an unbounded amount of data. Ingest and order is important. So all the work of managing those segments, we do internally to guarantee that that the application, when it reads data, it reads in order. And there are, out of this manipulation again of segments, we can do some interesting features that I talked about, like stream scaling, transaction for exactly one semantics, and so on. Pravega is under active development. It's an open source project already. You can go visit the website and see all the information there. We have documentation pointers and so on. And just to mention one piece of active work that we're doing that I believe is important is on the side of connectors. Pravega alone won't be very useful. You need to connect it to the rest of the world, in particular to stream processors, Flink, Spark, and even other systems. I know Hadoop is another system that we want to connect to because we still have batch jobs that we need to run. So there is a whole body of work that is going on about these connectors. Some of them we're doing ourselves, and some of them is being done by others or in partnership with us. So if there is any interest or opportunity to work on new connectors, we are open to doing it. And so with that, I conclude the talk. Happy to answer any questions if there is any.